welcome back. Apologies to the people who experienced some problems last Friday night with the homework. Some of you were still not properly signed on, so the late add-ons were experiencing some difficulties. I kept sapling on the ball with inserting your name on the list, and all of you by now should be there, so I don't expect any problems from now on. If you missed that homework session because of the sign-on problems, you will not be affected. Your grade will not be affected, so don't worry. Okay, so we'll take it into consideration when computing your final grade. Also, just to clarify, some folks said what's happening to the time of submission of the homework. It's supposed to be at 1 o'clock at night. That's not true. It's 11 p.m. on Friday. Okay, so 11 p.m. on Fridays is the time for submitting your questions. I mean, that's the final time. You can submit your questions. All right? Good. So we'll just roll on, and what we do is you actually take some of what we learned last week and talk, wrap up this particular topic, which is converting numbers, working with numbers, big numbers, small numbers, using the proper units, and doing calculations with conversions between units, and then in the end coming up with the right number in the right amounts of different things. So these are all steps and tricks that we have to manage. These are important tricks, as I'll show you in these examples. So, why are we doing this, you might wonder. Maybe you don't like to do all these things, okay, but these tools, these techniques of doing a calculation correctly, converting numbers correctly is of utmost importance in real life. This is not something we force upon you for fun. Okay, use an example. This is the Mars Climate Orbiter. If you are an engineer, you are maybe working on a project like this. Okay, so NASA built this wonderful thing, and it was supposed to go close to Mars. However, the thrusters didn't work properly, so close to planet Mars, they were given too much boost, so to speak, and this thing crashed in the Martian atmosphere. Okay? The reason was a conversion problem. They were mixing up the SI units with the English units. Small mistake with dramatic consequences. Okay, so this is a serious ordeal. Another example, the Gimli glider. This is an airplane, and something similar happened there. So the amount of fuel in this plane was calculated in an incorrect way. Okay? So instead of using the metric units, they used the English units once again. They didn't do the conversion properly, and there was not enough fuel in the plane. The plane was going into problems. Ran out of fuel, literally, and had to make some kind of emergency landing elsewhere. Nobody was hurt, but it could have been rather catastrophic. A simple, tiny mistake. Okay. Another example. If you are interested in becoming a medical doctor, you have to do your calculations correctly as well. Okay? Or if you want to be a nurse, if you want to go to nursing school, some of you may want to do that. These kind of calculations are very relevant for you. Okay, here's an example. This is a particular drug, phenobarbital, and this patient here got too much of it and died. Okay? Due to a simple concentration calculation mistake. All right? This is not a lone incident. This is something that happens a lot. Okay? Each year, thousands of patients die or have some serious injury due to miscalculations in terms of dose, weight, height, and so forth. Okay? So these things are useful. Sometimes on exams, students say, well, look, I got it almost right. Halfway through my calculation, things look still fine. In the end, I made a small mistake. And then finally, my final answer is 10 orders of magnitude off. Well, the method is still fine. And that's good. You get half the points for the method, but that can give you the full batch of points because arriving at the right answer is equally important than knowing some step along the way. Okay? In these kind of cases, it can have literally fatal consequences. So just to remind you guys, these things are not just for pestering you guys. Okay, these things are real. They have real implications. Doing things correctly is a good skill to have. And the better you're at it, the better your future employer will appreciate it. You say, oh, this person here does always a good job. Give this job to this person right here. This person takes it seriously. Okay, so much for my pep talk. Let's go to an example. We start at the very bottom again, okay, very simple. Homework 1 last week. There's nothing new here, nothing new. Just to kind of like get into this mode of doing things correctly and almost automatically. Repetition is key. Okay, converted the decimal number of this guy into standard scientific notation. Okay, well this should be easy by now. This is the right answer. I should blush you, sir. The reason why I popped this up is because these zeros here are significant. They are behind decimal points. They count. If you convert this to scientific notation, don't throw these guys out of the window. Okay, they are significant. That's why this is the right answer. These zeros remain. Slide over the decimal point 2 places. That's why it says 10 to the second. Another one. Convert a number 0.9 times 10 to the minus 3 into also a number that is written in scientific notation. Okay. Oh, actually, this is the other way around. This is something we have to write in a decimal format. So we get rid of this notation here. We write out a full number without 2 to the power 10. That's what they ask you to do here. So this is the reverse. This is the answer, 0.0009. So 2 to the minus 3 means you slide this thing over 3 positions to the left. Okay? You have to add those zeros. Those zeros are not significant. Okay? The significant number of digits, the number of significant digits here is 1. Only this 9 is significant. So everything in front of it is insignificant. That's why you can add as many zeros as you want. Okay. Another example. Still not very extraordinarily hard, but again, you have to start somewhere. This is about density. A pure solid has a density of this number right here. Densities are always mass per volume. So that's why the unit here is grams per milliliter. It could be kilograms per liter, or it could be grams per cubic centimeters too. All of these are units for density. The question is, what is the mass in grams of this much of the pure solid, expressed in the correct number of significant figures? Okay, so this is a volume. So what we have here, we have a density and we have a volume, and hence we can calculate the mass. That's what we have to do. So here it is. This is the formula for density, something you should memorize. Density equals mass over volume. Density is given, volume is given, the only unknown here is mass, which is exactly what I have to calculate. So I'm going to rearrange this formula like that. Mass equals density times volume, right? And then I'm just plugging in these numbers. So that's what I'm doing. Next step, I plug them in. I'm going to check what happens to the units. Always. I do it automatically in all cases, so I know that I am on the right track. This is the denominator. This one is just by itself. This one crosses out against this one. So milliliter crosses out. And the final unit is in grams. Okay, so that's good, because it is a mass that I'm calculating here. You just punch this into your calculator and you find this number, 405.8 grams, and have to check now how many significant figures do I need. This one has 1, 2, 3, 5. This one has 4. This is a division, and hence the final answer should be in 4 significant figures. That means after this 8, it has to disappear. This is 0. That means the 8 stays an 8, and this is my final answer. This is not in scientific notation. It doesn't say that here, so it's optional. You can either do it or not do it. That's optional. Okay? What is not optional, actually, is the number of significant figures. Okay? This is the same kind of situation. On exams, people say, well, you didn't ask me to put the right amount of significant figures in my answer, so I just gave 20 significant figures, 20 numbers. Okay? Well, that, the answer may be correct, but it is actually incorrect because those remaining 16 digits have no significance. And And if you put 20 digits on your exam, then I know that you have no clue about the significance of significant figures. Okay? So just don't do that. Even if the question doesn't say it explicitly, just keep these good practices and make them your own. Yes?
So for the answer, number of significant figures for the answer from the volume?
Yes.
Oh.
Yeah, this is the least precise measurement in my calculation. It has 4 significant figures. It means the answer should be in 4. Okie dokie. How about this one? Step it up a notch. Okay? This is also a density calculation. All right, so calculate to the correct number of significant figures. It says it explicitly here, but we should always do it. The amount of grams of sodium nitrate that are present in a certain volume of a solution that is known to contain 29 grams per 100 milliliter of solution. So what is the situation? This is, we actually will look at this very carefully in a subsequent slide. This is a problem where you have a piece of text with a lot of information in it. You have to read it carefully, slowly, try to understand what am I supposed to be doing here? What is the question? But I always like to do it just to filter out some information and write it kind of cryptically for myself. So for instance, I know that the solution that we're talking about here, 100 milliliter of it contains 29.83 grams. That's what it says. But I'm just going to write it for myself so I have more condensed information about my disposal. And then it says basically, what if I have not 100, but 316 of it? How many grams do I have? So that's the question. The question is, I have to calculate the mass given this. So this is kind of my summary, my executive summary of this piece of text. Okay? Everything else is kind of like fluff. I don't really have to focus on. These are the numbers I have to focus on. Okay, so this is actually a density problem. So what I'm going to do is this. I'm having here a volume and a mass, which means I can calculate the density. Okay? That's the first step I'm going to take. Density equals 29.8 divided by 100. That is this, 0.2984 grams per milliliter. Now, the density for this solution and the one that I need is the same. It's the same solution. I just have a different volume. The density is the same. So the density is this. The volume is given, and that means that I have density, I have volume. The only thing I don't have is mass. Okay? So mass equals, mass equals density times volume. I just calculated the density of the solution using this information right here. So density is given. This is the amount of volume that I want. Meaning, if I multiply these two numbers with one another, I should be getting the answer. Okay? The density I just calculated, the volume is the volume that I want. Milliliter is given, we'll cross out, my answer is going to be in grams. This is the number that your calculator says it should be, but it's not. Round it up to the right number of significant figures. Let me see how much I have. I have 5 here, I have 4 here, this should be in 4. So, 94.32. The last digit is going up by 1. Yes? Say again? This?
Yeah.
Oh, this should be a 3. Yeah. That's right, sorry. Yeah, this miraculously actually was lifted by 1. That is incorrect. Thank you very much. It should be a 3. And here it should be a 3 too. Doesn't matter for this, the digits still remain the same. But that's good, thank you. Good attention right there. Yes?
So, you don't have to significant figures that's in the actual equation, but you don't have to from that equation, first equations?
Okay, so yes. So this calculation, what I'm doing here is I just do multiplications and divisions in one stretch. Okay? Because this density here, I can just plug in this. The density is just these two numbers are divided times the volume. It's one calculation. I'm not going to make any rounding in between. I'm not doing any rounding in between. I'm only going to round in the very end. And so that's what I'm doing right here. Okay? So if the calculation is complete, if it's just multiplication divisions in a stretch, Don't round in between. Yeah.
It said 100 point milliliters without the other two zeros. Would you round to 3 significant figures instead?
If this decimal point was not there, so it says just 100.
100 point without any
If
zeros.
it has a point, it has 3 significant figures. If it does not have a point, it has only 1 significant figure.
So we round to the final answer to 3 significant figures instead.
If this will be, these 2 zeros will be gone, then your final answer should be in 3 significant figures. Yeah. Very good. Any more questions? Those are good questions, folks. I'm starting to like you already. Okay, so some practical conversions that are useful to have ready somewhere next to you. Okay? This first one, you have to memorize. This one is so important. 1 inch equals 2.54 centimeters that you just have to memorize that. It will come in handy as we move along. This one you don't have to memorize, but I'm listing it here anyway because for some of the calculations we need it. These ones you also do not have to memorize. Okay? If you need it, they will be given. But I want to have you guys a sense of approximately how much these numbers are relative to one another. Okay? Having a feel or a sense for these numbers is the best thing you can take away from a class. Right? And I'll say more about that as we go. The physical intuition of how much something should be approximately is key because it helps you approach the final answer and check whether or not your answer makes sense. All right, mass, pound and gram and ounce to gram. Again, useful calculations. If you need them in calculations, this will be given. So you don't have to memorize it by heart. But again, develop a sense of the magnitude of these numbers and how they relate to one another. Okay, so we're going to use these in a series of text problems. That's what we're going to do in the remainder of this particular lecture. Okay, so what is a text problem? I think you know it. We just solved one. But basically, it is a story or a piece of text from which you have to extract a mathematical operation. Okay? This is a very nice book that I read to my daughter often. 5 little monkeys sitting in a tree. Okay? What happens is there's 5 monkeys sitting in a tree. And then Mr. Crocodile comes along and snaps, and 1 monkey is gone. So it means I got 5, and I have 1 less. Okay? That's my mathematical interpretation of the story. Then it happens one more time. Little sister is gone. Then Junior, and then another little monkey is gone. Is gone. Very sad. And in the end, I got 0 monkeys. All right. Very sad story. However, in the end, I wish that you guys sense if I know that, but they actually are sitting behind the bushes. This crocodile didn't eat them. But this is my interpretation of the story. This is a very simple example. Of course, this is basically what it is. Read something and then translate that for yourself into a mathematical operation. Okay, now here's an example. What Indiana Jones. He tries to remove this thing from this pedestal. However, he's smart. He knows this can be easy. Okay? There must be a booby trap there. Of course there is. So what he wants to do, he has this bag of sand. Look, the bag of sand is about the same size as this thing. Actually, this thing is even bigger. So what he's going to do, he has this bag of sand and then whoosh! Very quickly, he puts the bag of sand in the place of this gold item. Okay? Question is, does he have a reasonable chance of not activating the mass-sensitive booby trap? Okay? Ideally, this should have the same mass as that. Now, let's look at this. The density of gold is this. The density of sand is much less, 2 grams per cubic centimeter. So, if they have the same volume, but a different density, they will have a different mass. Okay? Because mass equals volume times density. Okay? The volume is the same, the density is completely different. In fact, this guy is almost 10 times as dense as sand, which means the mass is 10 times more for this idol right there. Consequently, there's no chance. If that booby trap is mass sensitive, it will be feeling that the mass suddenly drops by a lot, down to 10% of the original mass. And naturally, the booby trap will go up. So this doesn't make any sense, basically. Then, in the movie, what happens is he has his idol, and then he plays catch with his friend. So they're throwing this thing back and forth. Okay? Now, assume that the gold idol is only 1 liter, which is ridiculous, because this thing is more like 2 gallons, something like that. Okay? But let's say it's 1 liter. What would be its mass in kilograms? Okay, well, this is a simple density calculation, in a way. I have volume, okay? I have density, which means I can calculate mass. Mass equals volume times density. I just have to multiply these two numbers. Okay? Volume times density. The volume is 1.0. The density is given right here. Okay? And I'll do this multiplication, but I already start using my conversions here. Because this one is in liters, that one is given in cubic centimeters. Okay? I want to convert the liters into cubic centimeters. 1 liter is 1 decimeter cubed. 1 decimeter cubed is 1,000 centimeter cubed. Remember, there's a factor of 1,000 between the centimeter cube and the decimeter cube. 1 decimeter cube equals 1,000 centimeter cubed. So 1 liter equals 1,000 centimeter cubed. This liter is going to cross out, and now I have my volume expressed in centimeter cubed. Then I can multiply it by this number, the density. 19.32 grams per cubic centimeter. This cubic centimeter will now cross out. Okay? And I get my answer in grams. So I've converted from liters to cubic centimeters, crossed out. I have my answer now in grams, but it wants to have it in kilograms. So the final conversion I'm going to do in this calculation is to convert from grams to kilograms. That means grams at the bottom, kilograms on top. 1 kilogram equals 1,000 grams. That is the definition. From that, I can synthesize this unit factor. This gram is crossing out. And I get my answer in kilograms. 19.32 kilograms is the final answer. That's about 40 pounds, quite heavy for throwing this thing back and forth. Again, an improbable event in this movie. Okay, another example. Something that is very practical, could happen to you. Let's say you want to replace the soil in your garden with these wonderful new formulas. Okay? Premium topsoil. So one of these bags, which is 40 pounds, can fill 10 square feet of ground up to a depth of 1 inch. Okay? So 10 square feet, 1 inch is like what you can fill up with one of these bags. My garden, though, is bigger than that. Okay? I have a plot that measures 200 by 300 meters. And I want to replace not an inch layer, but a 4 centimeter layer. Okay? So the question is, I want to go to the Home Depot and just calculate how many bags do I need? How many bags do I have to purchase at the Home Depot? A very practical problem. Nothing ridiculous by any stretch of the imagination. Okay? So how do I do this? All right. Now, what I have to do is to calculate the volume of this bag and the volume that I need in my garden, and then divide one by the other, and then know how many bags I need. Okay, so let's first start with number 1. I want to calculate what is the volume of this bag expressed not in inches and feet, but in meters, for instance, or centimeters. Let's do centimeters. The total volume of this guy. Oh, okay. Oh, sorry. Flip it around. I'm starting with my garden first. Okay, so I'm going to calculate the volume of soil that I want to replace in my garden. I'm going to do it in centimeters. I want to have my volume in centimeter cubed. Okay, so 200 meters converting to centimeters is this, right? This unit conversion here is 100 centimeters in 1 meter. So a meter will cross out. This multiplication will give the width of my garden in terms of centimeters. Then I multiply it with the length of my garden, which is 300 meters, same conversion. Okay? And then with the depth of the layer that I want to replace, 4 centimeters. Just multiply by 4 centimeters, because now everything is given in centimeters. If you complete this multiplication, the answer must be in cubic centimeters, which is the unit that I choose to work with in this question. 2.4 times 10 to the 9th centimeter cubed. That is the volume of dirt that's to be replaced in my garden. Okay. Next, I want to know what is the volume of one bag. Okay. Now, the volume is given in square feet and inch. So I have to evidently make some conversions here. Okay. So let's start with this feet thing here. 10 square feet. Okay, that is this unit right here. What I'm first going to do is to convert feet to inches, and then inches to centimeters. Okay? So that's it. 12 inches in 1 foot. 12 inches in 1 foot. And once you have converted to inches, you go from inches to centimeters. So 2.54 centimeters per inch. So if you just think for yourself that this square is not there. Okay? Forget about square for a moment. So think about the square is gone. It basically means that this square is also gone. Feet is going to cross out. Okay? Inch is going to cross out. And then my answer in centimeters. But this is not a length of an area. So the squares are there. But they are there for each unit. Okay? Thus, this square is also there and there. That's it. Okay? So these numbers have to be squared to do the calculation correctly. So it's 10 times 12 squared times 2.54 squared. That is the right conversion from feet squared into centimeters squared. Okay, so this is my area, and then I have to convert an inch into centimeters for the depth. Okay, so that is an inch converting into centimeters. This is the conversion factor, the unit conversion factor right there. Inch at the bottom, centimeter on top. I convert inches to centimeters. So now this is centimeter squared. This is centimeter. So then the total unit is centimeter to the third, which is cubic centimeter. So there we go. 2.4 times 10 to the 4th cubic centimeter. That is the contents of one of these bags. All right, so then I just have to make a division. Okay, this is the volume of soil in my garden. This is the volume in one bag. Divide one by the other, and you find you need a lot of bags. Okay, 10 to the 5th bags I need. So that's a lot. That's 100,000 bags. You have to go to Home Depot and buy 100,000 of these bags.
They're going to make you crazy.
I don't know. I'm going to give it a shot, see what happens. Okay. So, again, you know, a pretty plausible calculation. And if you take care of your units, do the conversions right, then you'll find the answer. Another one. It's about Thanksgiving and sleepiness after eating a lot. Okay, some people say the reason why you get sleepy is the tryptophan in the turkey. Well, let's see if that's true. Okay, so let's say you eat this much. Very conservative estimate. 1/4 pound of turkey. I know you guys eat at least 4 pounds of turkey. But this is very, by all means, somewhat of an how do you call that? An underestimation. Okay, so how much tryptophan do you actually have? Let's say tryptophan accounts for only 1% of the total mass of the turkey. Okay? So how many grams of tryptophan do you actually consume when you eat 1/4 pound of this stuff? This is not a really difficult calculation. It's a whole bunch of text, right? But really, the calculation is rather straightforward. So what I extract from this is the following. I will be needing this because I have to give my answer in grams, and it's given here in unit of pounds. Okay, so I need to convert it from pounds to grams. Okay, the mass equals the mass that's given, okay, in pounds converted to grams. Pounds at the bottom, grams on top. Pounds will cross out. I get my answer in grams. Okay, this is the amount of turkey you have consumed in terms of grams. Then I have to multiply it by 1%. 1% written in a fraction equals 0.010. Okay? This number divided by 100 is the fraction. So you multiply by the fraction that corresponds to 1%. You complete this calculation, you know how much tryptophan you consume in terms of grams. 1.134 grams. Let's check the number of significant figures here. I see 2 there and 2 there, so 1.1 grams is the final answer. Okay? So 1.1 grams then should give you at least a sense of sleepiness. And we can actually see if this makes sense or not. So let's turn to the next problem. A glass of milk. Let's calculate the amount of tryptophan in a glass of milk. Let's say you drink a quarter quart of milk. Assuming the tryptophan accounts for 2% of milk, which is not a bad estimation, okay? And assuming that the density of milk is 1.04 kilograms per liter, how much tryptophan do you consume if you drink this glass of milk? Which is typically not going to make you very sleepy. Actually, it gives you more energy. Okay, so I have to know something about what a quart is related to liters, because this is in liters here, kilogram per liter, this is in quarts, so the unit of volume has to be rewritten into liters. 1 quart equals 0.9463 liters. I'm going to use that. Okay, so what is the mass of the milk? Well, I have here density, okay, and I have a volume. So what I'm going to do is volume times density equals mass. The volume is given in quarts, but I have a conversion factor right here that I'm going to use to convert that. Okay? Then I'm going to multiply that by the density, and then multiply that finally by the fraction that corresponds to 2%. Okay, so here is the amount of milk that I have. This is the volume, quart converted to liters. Quart will cross out, always check. Always check that. Okay, if you cross out your unit. And my answer now is in liters, that's the volume, times the density. This is the density of milk. This is in liters, that's in liters. So a liter here, liter there, also crosses out, so my answer is going to be in kilograms. Okay, this much, 0.2460 kilograms of milk. I will multiply that with the fraction, which corresponds to 2%. Okay, this is the total amount of milk. The amount of tryptophan, which is 2% of that, equals 246 grams times this fraction, which is 2%. That number divided by 100 is the fraction of 2%, equals 4.9 grams. So, a glass of milk has 4.9 grams of tryptophan. A quarter pound of turkey has 1.1 grams of tryptophan. It's rather unlikely that tryptophan is the reason why you are so tired. It's probably because you just ate way too much. And your body says, please, let me sit down. Okay, another one. Lipitor. Lipitor actually is a very famous drug these days. It's against cardiovascular disease. People who eat too much meat, for instance, have high levels of cholesterol and got all kinds of funny diseases in their blood vessels, which we call atherosclerosis. It's not nice, and this Lipitor apparently is helping you out. Okay? It helps a little bit. The best way not to get cardiovascular disease is actually not to eat too much fat and meat. Okay, so all this stuff up here doesn't make any sense in terms of the calculations, just extra information. So forget about the first sentence, okay? And let's just focus on what do they ask here? What do they ask me to do? So I have a pill which weighs 2.5 grams. 4% of that is the active ingredient, Lipitor. What mass in kilograms of active ingredient is present in one bottle of 100 pills? Okay, so I have to calculate how much Lipitor do I have in kilograms if I have 100 pills. That's it. Again, this calculation is not tremendously difficult, but you have to accept that the value is correct. And I'll say something about this in terms of significant figures. Okay. The mass of the active ingredient in one pill, 2.5 grams, 4%. You just have to take 4% of 2.5 grams. So let's do that. 2.5 grams times the fraction that corresponds to 4%. Okay. And then I'm converting that because they want the answer in kilograms, I'm going to convert that from grams into kilograms. Okay, gram here, gram at the bottom, kilogram on top. 1 kilogram equals 1,000 grams. That is the unit factor. Right? Completing this calculation, I find 1.0 times 10 to the minus 4 grams. Kilograms. I'm sorry, kilograms. Okay, I don't have one pill though, I have 100 pills. So let's do that. 100 pills times this. That's it. Just a multiplication. Okay? So here I have my mass of active ingredient in 1 pill times 100, and you get this answer right there. This 100 is a count. Okay? It's 100 integers. And it's this particular situation, because it's a very definite count, there's no fractions or any kind, is infinitely precise. Okay? It's a precise count of pills. So this one is not limiting my calculation. This one is 2, which means the final answer is in 2 significant figures. Okie dokie. Let's move on to this problem. Another very interesting one. It's about alternative fuel. Here I have one that is called E85. It's called E85 because it contains 85% ethanol. The rest is ordinary gasoline. So you dilute gasoline with ethanol. So it's much more environmentally friendly. Okay. One drawback is that it produces less energy. So we have to figure out, are we better off with this fuel or not? Okay, so let's look at this. Assume a car gets 28 miles to a gallon using gasoline. And let's say the price, at least in this rendering of reality, is $3.5 per gallon. Okay? Right now it's almost $5 per gallon. I have to update this question. Okay? And for the other one, E85, it's 22.5 miles to a gallon, which is less indeed than 28. Okay, so it's less energy efficient. But the price is lower, $2.85 per gallon. How much will it cost for you to drive 500 kilometers using each fuel? So how much money do you have to pay in each case? Okay, this is a conversion problem. Okay, this is a conversion problem. So I'm going to use this. I'm going to go from miles to kilometers. Miles to meters in this case. So 1 mile equals 1.609 kilometers. Both use that. There it is. And I'm going to start with the cost of gasoline. I have to convert 500 kilometers into dollars using conversions. So let me show it to you that this is the exact same problem as we've done before in terms of conversions. Now this is a calculation you may be able to do because you drive your car a lot and you know how to do these calculations like intuitively, but let me show you how it's done in the way we are talking about right here. The same kind of method. 500 kilometer, I want to convert this kilometer first into miles because my fuel efficiency is given in miles per gallon. So, how many miles is a kilometer? I'm going to use this relation right here. Okay? This 1.6 kilometers in 1 mile. Kilometer at the bottom, mile on top. Conversion number 1. Conversion number 2 is from miles to gallons. Okay? Can I do that? Yes, I can. Here, 28 miles per gallon. That's it. Okay? So this is really a conversion problem. Miles goes on the bottom, gallon goes on top. So I convert distance to the amount of gallons used to drive that distance. And once I know the number of gallons that I burn, I can calculate how many dollars I have to spend. Okay? For that, I use the final conversion, which is basically based on the price of gasoline. Okay? So I want to go from gallons to dollars. That means gallons is at the bottom, dollars on top. Gallons will cross out, and my final answer is going to be in dollars. You see? From distance in kilometer to distance in miles, from miles to gallons, from gallons to dollars. All the other units cross out beautifully, and my final answer is in dollars. Because this is a scientific calculation here, I have to have 3 significant figures, not 4. Okay, so I don't know the amount of pennies here. The amount of pennies is insignificant. 38.8. Okay, let's do the same calculation for the E85 fuel. There we go. Exactly the same. Just plug in different numbers. 500 kilometers convert to miles, from miles to gallons. That's the fuel efficiency. You see miles will strike out. I have gallons now. From gallons to dollars, that's the price of the fuel. 2.85 per gallon. Gallon will strike out. My answer is in dollars. 39.4. That is almost $1 worse than gasoline. Okay? So, who cares about the environment? You care only about your pocket. You only going to buy that. Okay? Because we certainly don't want to spend 5% of our conscience on improving the world around us. Okay, last example before I let you go is about mercury poisoning. It's not a good disease to have. Your body basically breaks down. And we're going to calculate what happens, or how much of the stuff we have in a particular lake. Okay? There's a lake here which contains this concentration, 0.4 micrograms of mercury per milliliter. Okay? 0.4 micrograms of mercury per milliliter. I like this example because it's kind of, it shows you the way you present things have magnificent effects on your perception of how much something is. If I tell you only 0.4 micrograms per milliliter, you may say, hey, that's not. What is that? It's a minuscule amount. I can deal with that. I can have mercury in my body. Alright? But let's calculate how much of that actually is present in that lake. Okay, so here's a lake. The lake has a surface area of about 100 square miles. And the depth is about 20 feet. You know, decent sized lake. Decent sized lake. 10 by 10 miles, 10 by 10 miles, about 20 feet. That's a, you know, a regular lake. Not too big, not too small. How much mercury does it have in it? Okay, so let's do that. First, I want to calculate the volume of the lake. And I want to calculate that in a sensible unit. Okay? It's given in feet and miles. That's not really useful. And I'd rather have it in something that looks like a milliliter or so. Okay, so I want to go to liters or milliliters. So let's try to do that. This is the surface area in miles, and I want to convert miles into something that is a little bit more easy to work with. The first thing I'm going to do is convert miles to feet. Okay? And then multiply that with the depth of the lake. And there's many ways you can do this. I'm just going to show you one way. Okay? If you know how to do it, you can do it in a variety of ways. I'm choosing this route right here. Okay, so this is the conversion. 1 mile equals this many feet. Okay? So this is basically converting miles to feet. This mile will cross out. Because there's a 2 here, there also should be a 2 there in the unit factor. The unit factor gets the same power as the unit has itself. Okay? Do not forget. Now this mile to the power 2 strikes out, and I get this in feet squared times the depth. So now I'm getting a volume which is feet cubed. Okay? 6 times 10 to the 10 feet cubed. This is 6 because this 20 is only 1 significant feet. Okay, that's the volume of the lake in cubic feet. However, that's not really a convenient unit to work with still. So I'm going to convert feet into centimeters. Okay? How do I do that? 12 inches in a foot, and then 2.45 centimeters in 1 inch. Inch will cross out, so the conversion from feet to centimeters is 12 times this number. There's a 3 here. A 3 should be also in this, over the parentheses of this conversion factor. Okay, so this then here, this calculation here, gives me the volume of the lake in cubic centimeters. All right? Then I can convert centimeters cubed to milliliters. Why? Because 1 milliliter equals 1 centimeter cubed. So I have converted now the volume of the lake I've expressed it in milliliters, which is good because its density here is given in milliliters. Okay, so this is the volume of the lake. Volume times density equals mass. So if I multiply this by density, which is given right here, 0.4 micrograms per milliliter, cross out, I get my answer in micrograms. Okay, let's do that. 7 times 10 to the 14 micrograms of mercury. Well, that's an odd number still because micrograms is not really a unit that makes sense to us right here. I want to convert it into kilograms as is asked of us in the question. So let's do that. Here's the number again. I'm going to convert micrograms into grams. Okay? There are 10 to the minus 6 grams per microgram. This is like shorthand writing of the unit factor that converts micrograms into grams. Grams on top, micrograms at the bottom. There are 10 to the minus 6 grams in 1 microgram. Okay? So I have now expressed my number in grams, and then I'm going from grams to kilograms. Okay? 1 gram equals 1,000 grams. Sorry, 1 gram. 1 kilogram equals 1,000 grams. That means that 1 gram equals 10 to the minus 3 kilograms. Okay? So 10 to the minus 2 kilograms per 1 gram. This gram will now cross out, and my final answer is going to be in kilograms. So these last two, this number here and that number here, are conversions from micrograms to gram and from gram to kilogram. I'm going to write that out and find 7 times 10 to the 5 kilograms of mercury in the lake. Okay? That is actually quite a bit. That is 700,000 kilograms of mercury in that lake. All right? That is a lot. That's huge. That's like trucks dumping their stuff in the lake. All right? So this small number here, don't be deceived. That's a huge amount. That's enough, folks. I'll see you on Wednesday.